So let's continue. Now I'm switching to focusing more on the data. So it's about databases. We have seen already that you can work with data frames to organize your data. And the pandas data frames, they are organized in memory mainly. There are also data frames which go beyond the memory and stored on the disk. Another way to organize the data is to use databases, which in principle is a collection of tables that you can then do queries between and organize the data. So the workflow is a bit similar to what you do when you have a data frame, but you have now the resource remotely stored. So here is an example where we have animals and so describing the identities or some characteristics about animals, and then you look into what each animal has in the form of cellular structure, for example. So here you can see that animal 1 has type cancer, some kind of cell isotropy, and the volume is 1.0, and then you have a healthy one, and it's different. So you would have a list of this kind. And with that, you can start building up some queries. And that is done using SQL. Actually, it's written out as SQL, but pronounced SQL. And that is, I would say, the most known database system. And there are many different variations of it, but typically this is the language that is used for analyzing databases. And well, there are different variations: SQLite, MySQL, or Hive. And but in principle, it uses the same language. And when you do a basic query, you write up text like select volume from cells. And just going back to this table, we have the cells table, and here you want to extract the volume. Oops, wrong way. And then you get those. What you also can do is from average volume from cells where the type is cancer. So now we have already done some more selective work. So we only compute the average volume for those cells that have cancer. So that also accesses the database in a different way. You could also, of course, doing this using a pandas data frame, or you could do it in Excel. And actually, both Excel and pandas, they have backends to load data from SQL databases. But then you can also do a little bit more complicated things where you have several selections. So you do selections of the volume in the cells where the animal is from of a certain size. So that can also be done, and then you can do even more complicated, but then I'm not going to refer exactly to what it's doing because then I'm rambling a lot of things. But anyway, you can set up this, yes?
You would only use SQL for statistical information. You wouldn't like put the segmentation like a massive array in the
No.
database.
No, it's about storing the data. You can also store images if you like. It's then called a blob that you can do, but you don't do really image analysis. It's more about collecting data, ordering the metadata. Image processing, I don't think I've heard about in SQL. That's not convenient because the data is not stored in a good way for doing it. Then there are other alternatives called NoSQL, so databases where you can actually organize the data in a more scalable way. So, for example, the Mongo database, it's more about storing small pieces. Could be documents, the whole documents, images, etc., with some metadata around it. Or you can even go to working with graph databases, which build up a kind of a tree structure with the data, can be looked at into if you have a processing workflow and you want to see how it's developing, can be useful for also reproducibility or backtracking what you have done. And these can then be traversed with the graph search algorithms in a different way. So coming back to big data, we have already talked about that you have the 3 V's. We have velocity, volume, and variety. And here we have a lot of heterogeneity coming in, and we need to be performant, we need to be scalable, and we also need to be flexible. For that, we need to make sure that the scaling isn't a problem. So we shouldn't add more of our labor into working with 10, 100, or 1,000 images, but just let the computer needs a lot of time. It could even be you're starving for enough when you need even more data. That could be a thing. So in particular, when you do machine learning, you want to have a lot of data in order to build your models to be reliable. And of course, clicking is something that you should avoid to greatest extent, because clicking means a stopping point in your processing. Of course, you can have a single click or a few clicks in the beginning, but then leave everything to automatic work. Because if you need a stop point where you have to click and select things, the whole processing is execution performance is lost. And also reproducibility is also much harder to follow. A story from Google is that when they wanted to analyze their data and analyze the quality of pages in the search engine, they developed an algorithm called PageRank. And there are so many web pages out on the internet that it's not possible to run it in an efficient way unless they come up with something. And in principle, what they want to check every site on internet and check the rank compared to using this PageRank function. And that is how it links and how it's connected with each. And given that the number, you need to do it in a parallel way. So one way would be to split it up in different groups. And you could do it, of course, but it soon explodes into a lot of computation, because you have to do a double loop, because you have to do for every site for the current site, in every site on the internet, you have to check it. And then an inner loop, you again have to check for every site which ones are linked to this one, or the other way around. And that gives, in the end, some kind of current site rank. Problem with this is the complexity of n squared. So it has to do n squared times the number of sites comparisons to complete. And for that, we need to divide the task, of course. We can do a division into languages, for example, and then we run the PageRank for each language separately. But what happens if then we have a crossover between the different regions? Then this approach would actually crash. And if you would run this, with this complexity, it would take months to complete a single loop. And Google does that very frequently. I don't know right now how fast they do it, but they do it a lot in order to keep their databases running. So the next problem is if one computer or hard drive crash, then you would also have a problem. And well, you can always have a backup, but then you would need many backup computers. And the problem is when you come to having thousands of computers, it's not so feasible to actually have a backup computer for each. And then there could be the case that you have an earthquake and the whole computing center is lost. What to do then? And adding on even more complexity to the task is that the PageRank doesn't only count, it also keeps track of old rankings, and then it actually runs this algorithm until the ranks converge. So it's really massive, massive, massive computing. And here they needed to come up with a solution. And the solution for that, after a long story, we come to something called MapReduce. And it's a very simple concept where you have mapping, which applies a function to each of the sites. And you have a reduce, where you combine several sites. And here's an example. We have this data vector, and we want to compute the square. So the mapping of this function on the data would produce a new vector with just the squares of the data. The other one is reduce, where we do an addition. So we look at two elements and do some operation with the two elements. In this case, it's just an adding. And that can be done in different ways. So you can do it as a cascade like this. So you take the sum of 1 and 2, then you add to the add the 3, add the 4, and add the 5. This is kind of a sequential adding, but if you look at the second one, you can see that by permuting the data a bit, you can actually do the 1 plus 2 and the 3 plus 4, and then add those. And that means those tasks you can dispatch on separate computers, and then you have a gain. This one is just linearly parallelizable. I mean, you can just chunk up the data and apply each function each. So what we do is the whole MapReduce concept. It means that we can partition the data into chunks and send these chunks on different machines in the cluster. Then we apply the map. And there is also a shuffle and repartition of the data. And finally, we apply the grouping. And finally, we collect all the data and write to disk. And a task can be written in this kind of writing, where you have the data, you have the mapping, and you have the reduction. And that is called a job. And on that, you could probably also add an extra timing requirement that it needs to be done in a certain time. So what we do is the first part is actually doing a key value pair grouping. And that can be best described with counting words, where we have a data vector of a text document, where you have some texts, and the mapping part is actually splitting up the string into words, and then each word is assigned with a single one, and the reduce part adds all values for each word. So it finds all the words of, let's say here we have info. So every time info, it sums it up, and then every time expenses, it sums it up. And that can be described like this. So we have here two strings. We have cat, dog, car, dog. And when we do the mapping, we can see here that each of these strings get a 1. Then we do the shuffle and regrouping. We see that cat only has a 1, dog is now a vector of 3 times, and car is appearing twice, and then the reduce is then just summing how many we have of each, and then we come to the counting of each element. So this is how it's split down in this MapReduce scheme. And looking at a greater, larger example, we take the text from Shakespeare's A Midsummer Night's Dream and load the data. And you can see what the data looks like here, where you start with the title, and then there are a lot of lines. And then we start doing a lot of counting. Well, this one is only stripping down, so this is the how you would do it in the imperative way of coding. So you have a couple of loops, and then you check that everything is okay. Then the other way is, what does it say? Yeah, so then you can also get the output, then you count which ones are the most frequent and which ones are the least frequent. And then you see which words are mostly repeated and which very exotic words coming in here as less frequent. And this can, of course, also be introduced with the MapReduce approach using the task bags. And here we have the whole map filter and fold parts. And we can do it also in parallel, splitting up the data and iterate the whole thing. And that is done in a lazy way. So first we need to have a help function, which in principle just splits up the lines into words. And I'm not going to describe much about it, actually. Then we take this, create a task bag from the sequence of all the lines and say that it needs to be partitioned. So that actually says how large chunks we want to work with. And then we can see how to get these, this splitting with the help of line to word. That's the mapping part. It's actually using this function that splits up. And then it applies it, flattens it, and then we can get the top 10 and we can get the bottom 10, applying the lambda, which only tells that we want to look at the end of the array. And executing this, we can see what it looks like. There's a little bit of fancy wrapping where we can see the timing of extracting this. So it apparently didn't take that much time. And then we can see also getting this visualization, seeing how the cores were working on it. And with these task bags, we could actually even distribute it, if we had a larger file, distribute it out on more computers. So, looking for environments for distributed computing, we have different packages for doing that. Hadoop is one open source version of the MapReduce, which is released in the Apache project. And this is actually how many of the big ones deal with their huge amount of data. Then we have also Spark, which is a package which includes not only this MapReduce, but also machine learning support, and that helps quite a lot. And it includes the parallel computing without a lot of logistics library or compiling. It's you have it built in the system. And it also has the declarative way, so instead of telling a sequence of computers that need to be doing things and wait for each other, it does it as it's needed, and also in a lazy execution way. And another way is in the Python system, we have Dask, which is a pure Python system, and it aims at having a fault-tolerant and robust distributed computing interface to execute numerical Python code. And the good thing with it is that it has also port or similar interface as you have with NumPy, SciPy, scikit-image. I'm not sure about OpenCV, but those are for sure. And then you can also use them in Spark or Hadoop-like problems. So looking at it, we are going to work with these directed acyclical graphs, and we have that implemented in Spark, Dask, and even in TensorFlow and PyTorch, and that supports the massive computing. And well, here's a list of different of these resources that can be used. So you have to decide which one is the better. I actually don't have a top 10 list which one is to recommend. But look at one DAG. Is we work with images now, finally. We have small 5x5 images and use a single chunk. And image 1 has all elements equal 0, and image 2 has all elements equal 1. So very basic system. Here you can see that we have now a Dask array, which is similar to having a NumPy array. And then I add also this Dask dot, which is for the visualization of what I'm doing. So what I'm doing, I'm saying we have image 1 and 2, and it's DA zeros, so it would be the same as NP zeros. And special here is you define the size of the chunk. And then finally I show it, and then you can see what it looks like. Now we want to do a little bit more computations. So we want to do image 4 is equal to image 1 minus 10 plus image 2 times 50. And then you can actually write it like a normal equation line in Python with NumPy, for example. And then it looks something like this. There we have the two images coming in. You have a multiplication here, you have a subtraction, and then you have the addition, and then you have the output. So this is quite straightforward, some bubbles, but now let's do in some more complicated. Then you can see that now we want image 5 is equal to image 1 times image 4. And then you can see how this multiplication goes in here. And then we have the old scheme that we had before here. And then finally, we get our computation. Now, this is still a pixel-wise operation, so it's easy to split and parallelize. But now let's do some filtering on a 3D data set. Here we load a 3D image, which now is just here I show it in different ways. We have all frames summed up, so we have a projection in the Z direction, or we can also show 10 frames from it. You can see that there is a lot of bubbles. And this one, the image we want to work with is 100 by 400 by 400, and we want now to process this in chunks of 20 slices per chunk. And we also want to scale the intensity from 0 to 255 to 0 to 1. So then we get this array. We divide it by 255 to get the scaling. And then we say we want chunks in this format, and we call it foam image. And when we look at this data arrangement, we have now 5 chunks. And these will be filtered. And again, we just apply here, map on the blocks. We want to apply the Gaussian filter with some sizes and visualize it. And what you see here is that now every chunk is processed with the Gaussian filter. This could be good, but actually what we need to do is to do a better filter, because when you do filtering, you have boundary processing, and every boundary will give you some uncertainty in the processing. So what we need to do is to actually exchange between the chunks, and that's when it becomes this complicated. And that is, let's see, where is it now? So map overlap is the new function, and we want to apply the Gaussian filter. And the complication is that now we actually listen to our neighbors to get the information, to get a better filtering in the overlap regions. And that is why we have this get item part here, and afterwards we also have the overlap part. Oops. Yeah, and then we make it more complicated. We even add some binary erosion and thresholding, and you can see that this network is growing a lot and looking very complicated. But you can see that it's in some places it does a lot of crosstalk between the boundaries, and then it reduces, for example, when it applies. Where was it now? The trimming. I'm looking for the thresholding. I don't find it. But the idea is that in the end, after all these exchanges, you trim it and get down to the original size again. So now we want even to label. Then we need to create some kind of label function. And you want also, when you do the parallel processing, you want the labels to be globally unique, because otherwise it doesn't make sense. So here we need to add also some information about which block it is in order to bring this global uniqueness. And again, we do the block map of blocks, and then we can do the processing. And well, it took some time. Now, let's see. We can just look at these images and see how the processing was done. And then an important thing when you run these massive data processing, and you have to be aware what you're actually asking for, because there is an importance in which order you execute your task. So if you want for a quick preview, you want to just look at a single slice. Then is the question if you select a slice and filter it, or you filter and select a slice. You can see already probably from this illustration that this requires a lot more processing to do in this way. And I have this example. Let's see if I can run it now. Yep, I could load the data, and now I want to do the Gaussian filtering. And then we walk on and test here to compare the performance. And when I run it, you can see that the first one, which is filtering a single slice, it's much faster than computing all slices and then extract a single one. Thing is, if I start, so this was with a single worker, if I would add it to 8 workers instead, then you will see that it's about the same. But the reason is now that it actually, thanks to the parallel processing, compensates for the time lost. So In the first case, it's only using actually one worker, but here it's now using 8 workers, and then we get about the same time. So it is a little bit on how these task bags are splitting up the data and how it distributes it. So why it's going to take much more time if you do it a single way is that if you do the processing only on a single, then only 3 chunks are processed. And if you want to do it filter and select, then all chunks need to be processed, and then you extract the result. And then you have a much more complicated graph for that. So final part is about cloud computing. You probably know that you can buy computing resources, and that is actually a quite convenient way, because the computers you need are often quite expensive to buy. We have examples in our group where we bought workstations in the order of 10,000 francs. That's quite a lot of investment for a computer that you may use sometimes. But when you need it, then of course you need the resources, but you probably don't use it very efficiently. So instead, you can use these cloud resources, and then you just pay for the time that you actually use. And I actually don't know how it is here at ETH, but at PSI, we can buy in on these computing resources, and then you can actually have quite a lot of power for less money. Or else the other alternative is that you go to one of the commercial services, so like Amazon AWS, for example. They can actually, there you can specify, you can do a click list exactly what you need in terms of computational resources, and you pay it when you use it. And well, then you have these systems. They are based on, for example, a Spark system, where you can do k-means, matrix factorizations, etc. That's built into the system. And well, then you can also have commercial support on different systems. So we have a lot, all of these big guys, they provide this. And the thing with Spark is also that there is academic support. So all source code for Spark is available on GitHub. And it is actually pretty elegant. It's apparently implemented, at least at the time of these slides were written, about 20,000 lines of code, which is not much. And some PhDs may end up in 75,000 lines of code. That's pretty ambitious, to be honest. And of course, there is no patents or restrictions on the usage of this system. Then you can also go for the big data. So if you produce a lot of data all the time, you can go for streaming. And there you can start setting up post-processing goals, like you want to have the analysis done in a certain time, and you can also, throughout the data production, you can get time analytics and statistics on the performance and trends in the data. Of course, you can handle static data, but the important thing with the streaming processing is that you can actually bring it in when it's needed. And important is also that it's scalable, so you can connect more computer on demand when you need it. And important is also, when you work with streaming and very large data, is that you may only want approximate results. So instead of computing the average volume, average of a volume, you can say that give me the best volume you can get within 5 seconds. Or give me the average volume within confidence interval of 0.95. And these things, they of course don't give you the exact result, but they give the result in time when you need it. And that can be helpful if you want to tune maybe some processing to take a certain route, or also to shorten the time if you want to do debugging of something, just getting a hunch of how things work. So that was the end of today's main lecture. I will also give you a little, let's see, there it is. So a little wrap up what we have done over this week or over the spring. So in principle, why we do the quantitative big imaging is that we have some experimental data, and of course we have a lot of data and limited time, and also limited manpower, and sometimes even limited computational resources. And of course, we want to publish it. We want to have it in our master thesis, PhD thesis, or getting it out in publications. And therefore, we want quantitative analysis. We want it to be reliable and repeatable, and ideally also have automated, efficient workflows to work with it. So we need to understand the components of quantitative big imaging, so how the data is created, image processing methods, and how to work with the data. We also need to have at least some understanding of computer science and engineering, and finally, how to present the results, because in the end, you want to sell what you have produced. So this is the workflow where we look at images, we look at data, we look at filtering, we do segmentation and analysis of shapes, we're doing statistical analysis, and then we look into some extra specific task where we look at time series analysis or even combining data from different sources. And finally, today we looked at how to work with the computing. And in the first lecture, I was talking about what is an image, what operations we can do on our images. I also showed the histogram for a first interpretation of the data to get an idea what are we up with. And then I did a detour into other people's data, and also how we should prepare our data and what makes a dataset good or bad. Also important is the validation analysis and ground truth of our data for our datasets. Then in lecture 3, I talked about image enhancement, and before that, I actually introduced the topic of noise, and noise is present in all our images. And then I went on to how to reduce the noise in order to make our analysis more straightforward and less ambiguous, and also how we can use filters to enhance image features and even do orientation analysis. And then I came back to performance analysis. How good is the filter, or what should you watch out for when you do filtering, not to invent new structures. Then lecture 4 was about basic segmentation, how images are formed. It was first to understand what is the mechanism, how images are created, and what it means that something changed in contrast, and then basically how to apply a threshold using the histogram. This went on in the advanced segmentation, where we had methods to automatically find the thresholds in the images. And here we came up with also unsupervised methods, which includes histogram-based and clustering-based methods. And then also supervised methods that requires that you have some training data to tell your segmentation method first what it should expect in order to be able to segment the larger amount of your data. Part 6 is shape analysis. So now we assume we have segmented structures and we want to identify items in these structures and also analyze different shape properties and textures in the images. Then went on with complex shape. First part was addressing particle clouds, where you have a lot of small particles flying around and you want to do some analysis on those. And then went on to working on segmentation of touching objects. So the component labeling that we introduced in the previous lecture had the problem that when objects were touching, they were seen as a single large object, and with the watershed segmentation introduced here, we are able to separate those at the cost of possible over-segmentation. Another analysis is to look into the skeletons, which is the minimal structure of an object. And with that, you can also, for example, compute the tortuosity of a network. But important with skeletons is to know that you really need to prune or prepare data well. Otherwise, you have a lot of odd branches in your skeleton, which don't really make sense. So you really need to have a workflow that you prepare the data well in order to get nice skeletons for the analysis. Then statistics. First part was that there is no experiment without any uncertainty, and then I introduced some uncertainty analysis on image processing, then some probability and implications of statistical analysis. Here I also got into the visualization part, how to present your results in graphs in a meaningful way, and what elements you need to introduce in that. The dynamic experiments, then we went into the time scale, looking at different types of dynamic experiments, and also how we can do some time series analysis in terms of tracking, and also that you may need to do registration, meaning that things may be moving and you need to align them with each other before you can do your analysis. The multimodality imaging, again, I introduced now some modality combinations, and again here the registration is very important. In particular, it's tricky to have different types of modality because they have different contrast mechanisms, and that you need to build into your cost functions when you do the registration. Finally, when you have these, you can also fuse the data in different ways, depending on the goal of your fusion. And then I introduced some software engineering recommendation that you should actually promote the reproducibility of your analysis. You should be sure that your code is doing exactly that what you want, and unit testing is one way. The other is to have history of your development, so you can go back and see what you did maybe some months ago, and for that the repositories are very helpful. If you're coming up to doing larger coding, then you could also think about continuous integration, but that is more when you come into the large-scale analysis. I also actually added an extra tutorial around working with repositories. I don't know if any one of you saw it. I hope it's useful. It's actually not part of the lecture as such, but I thought it's good to have a little introduction in how to work with Git. Then today I was talking about parallel processing, distributed processing, and DAGs, how to work with larger data, and what problems that comes up with that. And well, then we had the project. The presentation is next Thursday, and those of you who do a project can have a presentation. 10 minutes is not so hard limit because there are not so many projects. So if you need a little bit more time, that's fine. But ideally, you should explain what your problem is and what your solution way and your key findings out of your analysis. And well, that's the end. There are no more lectures in this course. And for those of you who do projects, either now after the lecture or also make an appointment with me or Danny if you have questions. So thank you for coming here.